So calculated achievements that we made in our group is a screening system, so it's autonomous system by the DTH surgery. Unfortunately, we were not able to bring the machine along, but I hope some of you made it live a couple of weeks ago. Where we're essentially doing demonstrations throughout the entire week. We start with a medium-sized dog driven by highly compliant series elastic actuators. Better?
That's it.
Okay. All right, so it's essentially a medium-sized dog that is driven by highly compliant series elastic actuators, which means that you have full torque controllability. You can recover from pushes and pulls and also handle irregularities in the ground elevation. The current version comes along with an onboard PC and onboard battery, so it's essentially fully autonomous. Average power consumption about 300 watts, autonomy about 45 minutes, so cost of transport roughly 2.5. Now the cool thing for you is actually we sell this machine. So if somebody's interested, that's a special price for dynamic walking. So it lasts until tonight, 12 p.m. Now how do we control this? So for controlling, we essentially have a three-layered approach, which means that on the very lowest layer we do joint torque and position control. And this should kind of provide an abstraction so that people working with the machine can use it as a simulation environment. On top of that, we have behavior control, which translates certain objectives that you have. So for example, motions that you want to achieve, or also force distributions that you want to have into low-level commands. And on the highest level, we have the behavior planning. And I intentionally put here behavior as with this force-controlled machine, we can do much more than just planning the motion or executing the motion. One big thing is that this is a floating-based system, so we don't have direct access to where the base is and how it is oriented, so we need to have state estimation. Now, to make successful experiments with the machine, we have to do research in all these domains. Unfortunately, these guys had their poster presentations already on Tuesday, but still, if you have questions regarding state estimation, planning, or control, try to catch Michael, Peter, and Christian. I'll focus now a bit more on behavior control and present you one particularly interesting method for that, which is hierarchical inverse dynamics based on least square optimization. Now, what is a behavior in my eyes? Behavior is nothing else than execution of simultaneous execution of different tasks with different priorities. And these tasks can be, for example, motion tasks. We want to have certain impedance at a certain location of our body. We want to match certain template dynamics, or also keep just balance or move a foot point. Can also be objectives in torques or in forces. So for example, if you want to optimize efficiency or optimize, minimize the risk of slippage, these kind of things. And you see that all these objectives can be written down as least square problems or as optimization problems in general as a function of general accelerations, torques, and forces. And they are tightly connected through the dynamics equations of motion of floating-based systems. Now this means that essentially, as I said, behavior description as well as inverse dynamics is nothing else than a set of least square problems. And the cool thing is that you can solve this, for example, analytically by projecting each task-specific solution into the null space of higher priority tasks, or also numerically by standard QP solvers or so. So we applied this to Starlet, and I want to notice that you notice two things here. So first of all, everything is done experimentally, so we have to deal with real-world condition, which means modeling accuracy, sensor noise, and estimated floating-based system, so there's no external mock-up system for that. And the second point is that what you do here is a pure task-based feedback. So there's no low gain or position, there's no low gain position control group running in any of these experiments. So we started with static walking, which is in fact not very interesting in terms of the motion that you can do. But what is interesting in static walking is as you're moving only one foot at a time, you have at least 3 legs in ground contact, which means that you have a lot of internal direction that allow you to optimize the load or force distribution without changing the motion. And we did that in a couple of experiments and evaluated, for example, the energy consumption or also the risk of slippage. And it turns out that depending on the optimization objectives that you put on these internal forces, you can, for example, lower the energy consumption by roughly 15% or also decrease the risk of slippage. And the cool thing is that you do this without changing the tracking behavior. So this means that depending on the ground or depending on the objective, you can use different kind of optimization strategies and get a different behavior. Another cool thing is that you can also include inequality tasks. So what you see here on the left side is the motion, so the coronal motion of the main body. Then you have here the rotation of the main body, torque at the hip joint, torque at the knee joint. And now for some reason, we say, for example, we want to limit this to 10 Newton meters. So we include inequality task in the whole thing, and this is the output. So what you see in blue is essentially that the torques look exactly the same. Again, this is experimental results until you hit these limitations. What happens then is that other joint turns in, they take over part of the load and support this thing, while the motion is exactly the same as before. The same holds also for position tasks. So for example, we command here a base shift, so go from that configuration into this configuration, and without violating certain joint limitations that you have here at the hip, as one artificial example. So we have our task priorities, and what happens if we introduce this inequality task that this should not be violated is that the task with lowest priority cannot be satisfied anymore. So the robot shifts its base forward until it hits this limitation, then starts violating this lowest priority task. So it increases the body height, still shifts forward, and hence maintains this angle limitation. You can also change priorities, and that's the output. So we hit the limitation, and the robot starts tilting its main body such that this angle limitation is not violated. Another thing is that in leg locomotion, we always have these transitions between different legs. So one leg lifts off, the other one goes down, which often is accompanied by discrete switches in the contact forces. Now we can use these internal directions essentially to do preparatory unloading, to distribute the force in such a way that you get smooth contact force and also smooth joint torques, while at the same time, again, motion remains exactly the same. You can also go to rough terrain, or let's say to moderately rough terrain. So what you want to have here is you want to align the contact forces with the local surface normal. So what we do in our weighting function, we include the local tangential directions. So this means that the robot applies the forces in a normal direction. That's the output. So what you see here on the left is essentially walking without knowledge about the ground. So the robot starts sliding and slipping. Now on the right side, it knows about the environment, applies internal forces, and literally clinches to the ground. Now the same thing can also be applied in dynamic gaits. So the only thing that we change here is essentially the gait pattern and the oscillation at the main body. So everything, all the rest remains exactly the same. So we have the same priorities, we have the same gains. Only thing, the gait pattern is changing. Now, in difference to the static walking gait, we have now an underactuated situation. So we have the two diagonal pairs of leg in ground contact, which means that we can't generate any angular momentum around this line of support, such that footstepping is getting more important. So we have to recover in forward velocity and sideward velocity by placing the foot at an appropriate location. The other thing is that still, although we are underactuated, we have internal directions, which means that we can distribute the forces in different ways. And also here in dynamic gaits, we see that risk of slippage can be optimized, or the energy consumption can be optimized. So different objectives that we can, depending on the objective that you have with the entire robot, can be satisfied better or worse. So I want to stop this presentation with a selection of movies. So what you see here on the top is a dynamic trotting, with the only thing that we changed the oscillation at the main body. And it gives a completely different appearance to the entire robot. Here you see pushes and pulls, so essentially the robustness of the system against external disturbances. And here on the right, walking over rough terrain. So thank you for your attention.
Questions from the audience? So, if I understood you correctly, you use prioritized control. You try to do 100% of something, and if you have a little redundancy or freedom left over, you'll try to do something else. In contrast to the intellectual approach is to just have weights on everything and throw it into one big optimizer.
Yeah.
and you'll trade off one thing against another. And the nice thing about the optimization approach is you don't have this discontinuous behavior of you try to move forward, you hit a constraint, and then suddenly you dip down. In optimization, you'll sort of be dipping down all the way.
But this doesn't include that.
Yeah, okay.
Exclude that. So it's
why use prioritized approach?
because there is certainly some tasks that have much higher priorities than others. So for example, I never want to fall down, while other things like looking somewhere, grasping something, or things like that are not important. So if you put everything in the same optimizer, what happens is that your weighting matrices is getting not very well conditioned. So you have extremely high weights on one side and extremely low weights on other things. Now with this priority, you can circumvent this and have a pretty nice structure in one way. I mean, if you want to have this on the same priority level, you can certainly do it. So you have this freedom. But still, this gives you the opportunity that you give higher priorities to some tasks and lower to others.
As a side comment, it failed as an economic approach for distributing goods. We use money and prices to continuously allocate goods. And I would argue you should be using money and prices to allocate resources in your dog.
Okay.
Capitalism.
What's the fail part to that?
Communism. You guys get shoes, you guys get rice, you guys get umbrellas.
Chris, we also have laws like you can't sell crystal meth.
Catastrophic prevention law.
So it would seem like a combination.
Capitalism.
More questions?
I mean, then I have one, if I can. So, I mean, is there need for something like this? So, I saw a lot of controllers here at this dynamic walking conference, a lot of theory, but only few of that was actually really shown that it's working in hardware. So, if this thing could be provided to others, so would people really like to have that, or would people want to run their stuff on real systems?
You want to have the hardware.
If you want it.
Yeah,
That's the question.
So I argue that what we, as a field, need to be thinking about from now on, we need to stop thinking about gait and the lower body. We need to be thinking about whole body behaviors. And I would actually try to sell this thing by getting it to do dog tricks, like stand on two legs. Is it strong enough to stand on two legs? Because then you sell it, look, this is a biped, it could, you know.
That's because you want to have bipeds, right?
No. It's because I want to use arms and legs and the head in a coordinated fashion. And I think that's, we have to pull ourselves up from this incredibly low level of just walk or run. And
But you're not even able to do this now. I mean, you're not even able to do this so far. So to locomote in rough terrain autonomously, so without external mock-up systems and knowledge about the terrain. So nobody has shown this so far. So
there's a long tradition in science in declaring victory and moving on prematurely.
Which is what you're advocating, right? I suggest right.
We should be doing that. But the way I'd sell this thing is, you know, I get it to do a variety of behaviors, including, say, vertical rock climbing, and to the extent possible, you know, turn it into a biped with arms. It would sell like hotcakes. Capitalism.
What type of communication interface are you using to control the robot? And like, what processing is done on board, and what's done via some remote PC? Like,
So right now everything is on board. So it's a standard Linux PC that's running on board. It has 4 CAN buses communicating to the motor controllers in parallel, and sensor boards as well. So that's the setup essentially. And then right now, I mean, you have a joypad or joystick or gamepad where you can just drive it around. I mean, high-level commands. Planning is not included yet. This is things that need to be done in the future. So right now, the human is there commanding, okay, go forward or turn or do whatever.
If I were to buy one, are you guys supporting it as like a company, or like if it breaks down, do I have to fix it?
I was just wondering if there is interest for things like that, because there is a lot of theory around, a lot of controllers around, but not a lot of showcases. Here's something people should maybe think of.
I know you're in Switzerland, but the NRI has a strong interest in supporting common platforms, as I learned from a certain presentation the other day. So, just saying.
Okay.
Thank Marco. The next speaker.
I'd like to acknowledge my co-authors from Germany, from the University of Erlangen and the Adidas company. So the motivation for this work is predictive simulation, which Scott Delp talked a lot about on Tuesday night, with applications in the medical field as well as in sports. So in both of these fields, you're designing a mechanical system that is coupled to the human body, and it would be really nice if you could predict how humans respond to that, how they alter their movement before you make a prototype and test it on a lot of people. And the goal really is to have an early evaluation of new ideas and design concepts so you can quickly determine whether you're going in the right direction. And modeling and simulation is a very cheap and easy way to do that potentially. Just a bit of background. So trajectory optimization on musculoskeletal systems. You start with a model of musculoskeletal dynamics. And then the way I do it is I define it as an open loop optimal control problem. We are trying to find state trajectories and control trajectories as a function of time to minimize a certain cost function. And the answer would be trivial if you didn't have any constraints. So you need to satisfy, of course, the system dynamics. Usually you have bounds on the controls, and then there are task constraints. And that's actually very important for me because I want my system to perform a certain task exactly. For instance, if I try to predict the energy cost of running and the effect of a running shoe, I won't allow it to end the gait cycle with a little bit less kinetic energy than it started with, because that would be an easy way to reduce the energy cost. So typically for cyclic movements like walking and running, the task constraints look like this, that your state at time t has to be the state at time 0 plus a forward translation in state space. And the way we solve it is with direct collocation, and I won't go into the details of the method. There's a paper there cited that you can look up how we do it. So something we published last year was just as a proof of concept that you can predict the effect of gravity. And it has some features that, the predictions have some features that look real. But we also identify some problems there. Interestingly, though, on the moon, it predicts that you would start skipping as the solution that gives you the least fatigue. Two problems. The initial guess is very critical for the success of this. So you need to start with a pretty good guess of what the solution will be. It's inconvenient, and there's a potential for bias in the result. You might bias it towards your initial guess, and you might never discover other solutions. And the prediction of walking on Earth, what you see on the left, wasn't really that good. It has some things that people don't actually do. So we went on to do some improvements for more practical applications. And first one was in the numerical methods. And instead of explicit differential equation, we formulate now the dynamics as an implicit differential equation. And that has a lot of advantages because in muscle models and in musculoskeletal models, you have some near singularities that make it really numerically poorly conditioned if you solve the state derivatives. And in the collocation scheme, this works just as well as the explicit formulation. And the second is for the cost function, we started including a tracking term which encourages the model to move like a normal person. And there's still a cost for the control, so it will not try to emulate a normal person at all costs. And that's, of course, what it makes it adapt to a thing like a shoe or a prosthesis. It will start deviating from the movement that it's trying to track to reduce this control cost. And typically, the control cost is more important. With this, we managed to do a study on the effect of masses on the leg, on the energy cost of running. Here are some results. So, for example, if you attach 200 grams to your foot, you get an increase in energy cost of 2%. And that matches exactly what's been measured with metabolic energy. And also kinematics. Stride length is another parameter that has been measured in humans in these conditions. And those predictions were very good as well. So we were happy with that as kind of a proof that there is some value in doing this. But before we could do anything with footwear, we had to do something with the contact model. Because in previous work, we always had a penetration-based contact. So you could simulate elastic properties of footwear a little bit with that vertical. But horizontally, it was just friction. So it was sticking or slipping. No deformation. And that's not how shoes work. So we then moved to a model where you have an elastic connection between the rigid body and the point that actually contacts the ground. And that's a model that's suitable for footwear-related questions. It's also more realistic if you consider soft tissue between your bones and the ground. Oops. So in a planar model, that just leads to a few extra variables in the optimization. So for each, was that the bell? No. Okay. Okay. The position of the contact point and the forces acting on the contact point become 4 extra state variables at each contact point, at each point in time in the optimization. And then also 4 extra equations. So there's a 2D load deformation relationship between the point and the rigid body. And then equations for the contact between this massless point and the ground. And I thought this might have some numerical advantages. We have more equations, we have more variables, but possibly these equations are not as nonlinear as the penetration-based contact that we were using previously. And the Jacobian matrices may be better conditioned. So I wanted to see how critical the initial guess is and how fast does it converge. And so I ran some tests, and that's just to kind of investigate the methodology a little bit and the performance of it. So walking at a fairly slow speed, only use the effort cost, so not the tracking. We're not trying to answer real-world questions here. For those of you who do this sort of thing, it's a backward Euler discretization and using the IP-opt solver. So first, with an initial guess that is kind of intelligent, such as first let's track human movement and then re-optimize it with the objective of only minimizing effort. That takes about 1 to 2 minutes, and a result comes out that looks like what I've shown before. And then the other way is to just try standing. It's very easy to predict with minimal effort, and then successively increase the walking speed and each time re-optimize it, and gives exactly the same solution. But I still think this solution might be biased by an initial guess. We don't know if there might be even a better solution somewhere else. So let's try a random initial guess. And I sped this up 30 times, so you can see the 7 minutes of this optimization run in 14 seconds. So that's top left, you see the gait cycle represented as a stick figure. It starts out being random. The constraint violations go down, and the objective goes down. And then after 7 minutes, a gait cycle comes out that's totally predicted from scratch, from a random initial guess. And I should not rewind it. Let me just play that again. You might have noticed at the end, the solution was a very solution where it stands on its toes. So it's a tiptoe type of walk. And I see that a lot, and fortunately, those are not the lowest cost that it can possibly get. So it's clearly a local optimum. So because it takes only 7 minutes, I did 19 of these runs, and 3 of them did not converge to a solution. 3 found that same solution with cost 0.07 that I also found before. And then there were 13 locally optimal solutions with a higher cost. And you see one on the right there. So it does several little steps, and then it does a symmetrical thing on the other side, and the cost is higher. So I find a lot of those local optimal solutions as well. So discovering strategies for novel tasks, I think, might be actually possible with a random initial guess. So just as a quick test, I did made my task constraint like this. After half a gait cycle, you need to be at the same place where you were before with a mirroring operator, forward translation, and then a 2-pi rotation of your trunk. So you require a full somersault in each step. Of course, the task must be feasible for the system. And I couldn't discover it from an intelligent initial guess. But when I kept restarting it with random initial guesses, it actually did find the solution to the problem. So I think a gradient-based direct collocation approach can actually find globally optimal trajectories if you restart it often enough. I'd still like to improve that so that it's more successful or more frequently successful. There's still some issues to be addressed, just scaling to higher dimensional systems, movement of longer duration, and hopefully the computation time and the sensitivity to initial guess is still acceptable. The contact model is a bit of an innovation that we did, so having a massless contact point actually works, but I'm not quite happy with how we did that, so I'm looking at Michael Posa's paper from last year and trying to use his equations. Thank you.
Questions for Tom?
So to what extent that big term said about tracking human data,
Yeah.
how you said that didn't come into play very much, but could you elaborate upon that?
Yes, so it's the matter of the weighting. So I make sure that the weighting of the effort term is high enough that the tracking is only used to eliminate really crazy solutions, those locally optimal solutions that I don't like to see, so that it can deviate from that movement that it's trying to track quite easily, but it cannot do something really crazy.
So in your optimization, if you go from point A to point B, do you define any desired trajectory, or it's just you tell it the initial position and the final position?
I don't even tell it the initial or final position. I allow it to do anything. I just define the task as whatever position you start at, you have to end at with a forward translation.
So what? So it seems like this. The idea here is to have this simulation in the loop of a design process for something for
Early on, yes.
Early on, yeah. So can you tell us a little bit about what that loop is? Like, so you can try out different shoe weights or different.
It's at the conceptual stage. So in shoes, there are a lot of elastic structures that they can put in under the shoe, and they don't have a huge effect on human motion. It's very subtle, so it's very hard to figure this out just by thinking about it. But if the effect is only 1% in energy cost, that's still very significant for sports-related questions. So very early on, you have a concept for what you might want to put in a shoe and then try it out in simulation. If the energy cost goes up or down, that's really the main question initially.
So you may be, I mean, I can't think of another example of this, but where you're like a human in the loop simulation of a product that might actually be for sale at some point and be beneficial.
A human in the loop simulation.
Well, I mean, sorry, not a human in the loop.
Okay. A model of a human. Yeah.
Model of a human in the loop of the design process.
Yeah, so for prosthetics, for instance, I have a project where I use it for prosthetic design. So you can change the mechanical properties of the prosthesis and even the control system and try to predict how the human would function with that, because the two systems are coupled.
And where people are building things based on that?
Yeah, we're trying to.
Yeah. Okay. More questions? Go ahead.
How do you model negative muscle work in effort-wise? And does it really affect your simulation?
Well, it happens. I don't model it, and I don't. When I evaluate the results, and I don't do metabolic energy. I just look at mechanical energy of muscles, and I only count the positive work. That's what I did in the, and the ones with the weight on the shoe, I only counted the positive work. As a very simple outcome measure.
So I'm a little bit skeptical of modeling in for the design process, because it seems like there are always things that the human does that are hard to account for. And I guess an extreme case is Deanna Gates was talking about doing a study with a prosthetic foot, and one of her subjects refused to wear it because he had these skinny jeans, and he couldn't wear this foot with his skinny jeans. And so it just seems like there are all sorts of weird things that happen. I guess more locally common is we'll build a device and then it's uncomfortable in some way that causes blisters or digs into somebody's skin or something like that. And it just seems like the mechanical function is the least of our worries in the design process for something for humans to wear.
Yeah, so there's a lot of things that you could never predict, of course, but there is a lot in mechanics that you can predict that might be important. So in the prosthetics project, I was looking at design of a knee and trying to make it function more like a human knee, producing the right torques and everything, and putting it in this full body model. I was running these optimizations, and the knee would never produce the torque, even though it had the capability. And it turned out that the prosthetic foot was just a passive foot, and so the knee didn't really have a good way to perform its function. So this optimization predicted that even though the knee had all this capability, it was fully controllable, it didn't produce the torque because. So there's some things that you can. I'm not sure that that's the right prediction either, but some of those insights, they can come from this, and they have to do with mechanics. Yes, yes. What's important, then, in which direction does it go? And I'm not really designing based on this, because that still requires a lot of other.
Well, like, it sounds like you're saying, like, don't use SolidWorks to design something mechanical, too, because you're not going to know how it feels when you put it on.
No, because SolidWorks is a correct rendering, or a pretty good rendering of mechanically what's going to happen. And it's not claiming to tell you what the human's going to do.
So this is intended the rendering of the biomechanical system, not the
human.
Not the human.
But not to let you go on this, but if you're always going to have these things you're not going to be able to anticipate, whether or not you're using SolidWorks or to do something mechanical or this or something, this 10 years from now, right? There's always going to be unanticipated things. In anything. Why not?
Because SolidWorks is pretty good. And then there are cases where, so we use SolidWorks when we are pretty confident that it's going to be a pretty good model of the mechanics. And then there are some cases where models are pretty bad. So pretty much anything that involves friction is pretty bad. And luckily, so in mechanical design, we know that. So I think in general, in mechanical design, we try to go for as close to zero friction as possible, or as close to infinite friction as possible. And then there are only a few devices that are sort of in the middle of, they need an intermediate friction in order to work. And then that takes a lot of effort to do. And then probably less model-based, but more iteration-based. So like clutches in cars, have had a good 100 years of evolution before they became good. And I'm still not sure whether they're good models for that. But then people don't, when models are not good, they just don't use them.
Right. So I think you've got to be careful what questions you use your models for, right? These models have limitations too.
How stiff are the springs using for your foot contact? And if they are stiff, how does that kind of impact the desire to use coarse concepts?
They're representing soft tissue and footwear. So in their full body weight, they deform about 10 millimeters. And the stiffness doesn't really matter as long as there's some damping in it. Or you use a numerical method that introduces some damping. With the collocation, you can use big time steps, and the spring will basically find its equilibrium when it's not, loaded, because that. It would, yes, because there's no mass, and if there's no damping, it would find its equilibrium instantaneously.
Is there a reason why you only account the mechanical work of the muscle and not the metabolic concept?
Just that I haven't gotten around to doing that yet. Somebody said earlier in the week that the predictions don't seem to be sensitive to that, but I've seen predictions based on metabolic cost that look a lot better than my predictions based on muscle activation. So I think I do need to try that.
Take one more question while we're switching over. Okay, you can sit the same time.
So I'm going to talk a little bit about muscle contraction. So the first thing I thought I'd do was motivate why do we care about muscle contraction. And sort of I decided to list my 3 motivations. And the first one is that, I mean, it's a biological process. It's interesting because it's there. The second is that obviously we want to understand locomotion and we understand why people move the way they move. And maybe minimization of metabolic cost is a useful thing about that. And maybe we want to cure disease. But I'm going to make the argument that Hill models and things that look, at least at the present level of Hill models, can't do any of these things. We can discuss that later. Okay. So where do you go? How do you attack this? And one particular way to attack it is to think about what the molecules in muscle are doing. So muscle is this multi-scale system. So if this is a muscle, it's made up of fibers. Fibers are made themselves up of little fibers, which themselves are made up of these filaments. And these filaments are molecules. And it's these molecules that interact that drive muscle contraction. So 50 years ago, Andrew Huxley came up with a very simple way to relate this molecular scale to this large scale. And the basic idea is, so here's his cartoon model that I redrew from his paper. And it's meant to model this molecule here. In the next slide, it'll be switched around, but everything's the same, basically. So here's that model again, and the idea is that you have some little micromechanical system, but that micromechanical system has some chemistry. It can bind to this binding site, it can unbind from this binding site, and it does so with some particular rate constants. But the thing that makes it sort of interesting from a chemical point of view is that these rate constants depend on where the binding site is. And if you think about it, if you're a muscle, what you want to do, if you have this little mechanical system, is you want to bind when it's over here, and you want to unbind when it's over here, because that way you move everything that way. So what he did is he said, let's make it do that. And so he made an attachment rate, which I call Ka, as a function of x. X is the position of that binding site. And it increases in this direction. That's the binding, so it's more likely to bind there. And then it decreases to the left. So it's, it goes to 0 to the left, and the unbinding rate, Kd, is large to the left. So it unbinds there. And it does roughly what you want to do. But the main point is that if you have some chemical model, and if you describe how these rate constants depend on the position of the binding site, you can write a differential equation for the probability of finding one of these systems bound. And if you assume they don't interact, you assume you have a large amount of them, then this probability describes everything you'd want to know. It describes force, it describes ATP consumption. So it seems like that's a good thing. And it turns out that these kinds of models, so this is the state of the art 50 years ago, people have and are still making advances in this kind of idea. They do some things very well. They can get steady state force velocity, they can get some force transients. Basically, if you do an experiment and all you look at is that experiment, they can do that very well. But the problem is if you want to get all muscle phenomenology, they don't work so well. And there's some things that actually they don't do at all. They don't do forcibly lengthened muscle very well. They don't do submaximally activated muscle very well. Their hysteretic properties of muscle they don't get very well. They don't get fatiguing muscle. They don't do energetics particularly well. And part of the problem is that you have these attachment and detachment rates that you can just make up. Right? Those are just curves that you specify. So wouldn't it be nice, and this is the goal of my work, is to actually look at molecular measurements and specify these rates based on those measurements. Okay, so what do I mean by molecular measurements? So the past 20 to 30 years, there have been incredible advances in what we can do at a molecular level. So here's one particular experiment. So what you're looking at is individual myosin molecules. These are the molecules that are involved in muscle contraction. And you're looking at individual actin filaments that are moving over this dense bed of myosin. This is what the experiment looks like. And these wormy things are actually the actin molecules that are tagged to become fluorescent, and they're moving over myosin. And sort of from a cartoon picture, this is what's happening. You have these molecules, they're binding, and they're moving the filaments along. So that's pretty cool, I think. There's another really, really cool experiment, is you can take a single myosin molecule, you can take a single actin filament, and you can attach beads to the end of the actin filament. You can hold those beads with lasers, and these beads being very small, they're about a micron across, they dance around due to Brownian motion. When myosin binds, two things happen. It changes the mean position of your signal, but it also strongly decreases the variance of the signal because it increases the overall stiffness, and you can measure it. Here's my cartoon of what's going on. There's real data. And so what you can do is you can vary things, and you can see, well, how does that step change? How does myosin's individual step change? And how does the duration of that strong binding, how does that change? There's other really cool things you can do. And this is, to me, an amazing experiment. You can detect as soon as myosin binds to actin, and you can apply a force. So you wait until you detect binding, you pull on it, and it turns out that unbinding rate then changes. And it changes roughly exponentially, so you can do a 2-parameter fit to the data. These are two different experiments that are measuring the same thing in slightly different ways, and the point is they're roughly the same curve. You can predict the equation that should fit it based a little bit on the statistical mechanics of what's happening. But to me, this is really cool because now this is that x dependence of those rate constants. This is the thing that people are making up and drawing, but we can actually measure it. So the idea of the work that I want to present is we know all this. We know all of these chemical steps. We know roughly what's happening at a molecular level. We know that this step and not these other steps depend on force, or at least we think that. So based on everything we know, what kind of predictions can we make? So again, that's this slide. So we're thinking about what's happening in the single molecule, and I want to validate it not at the level of whole muscle, because whole muscle is very complicated, but I'm going to validate my model at the level of these other experiments. I'm going to go through some other experiments that I didn't talk about to show, to test the model. Okay. If you're interested, it's published here. Okay, so muscle comes in a variety of different flavors. There's the muscle in your gut that causes gastric motility is very different from the muscle that powers your motions. And it turns out we know a little bit more about the muscle in your gut just because it's a bit easier to work with experimentally than the muscle that powers your movement, so perhaps we care about that more. But the idea is that here are the parameters of the model for skeletal muscle, the muscle that powers your movement, and smooth muscle, the muscle that powers your gut. And I don't know one over here. I'm going to assume that, and this is the stiffness of the myosin, I'm going to assume that once I get this thing to work, that it's the skeletal and smooth have the same stiffness. There's some evidence for that. And then if I can do that, then I'm going to have 2 parameters for my skeletal model. Okay, so basically I'm doing a 1-parameter fit for smooth and 2-parameter for skeletal, but I'm slightly lying to you because when we go on to further experiments, I won't know the number of molecules. So that'll be an extra, a hidden parameter. And I'll talk about that when it becomes relevant. But so since the model is based on single molecule data, it better be able to fit single molecule data. So here again is that experiment. And what we're looking at over here is measurements of the length of the binding as a function of ATP concentration, so you can change the ATP in these experiments, and it is predicted to lengthen the attachment time, the time of these events. And sure enough, it works, as you'd expect it. You can do these larger ensemble experiments. So this is this motility experiment that I showed you earlier. You can get for smooth and for skeletal, you can get these are busy. Look at the hollow dots, which are the model, and the black dots, which are the experiment. So the model fits the experiment. There's another experiment where actually you change the number of molecules that are interacting with the filament by changing the length of the filament. So if you look here, for a short filament, only a few myosin interact. For a longer one, you get many. So if you track filament length, you get some relationship, and the model fits that. There's one more experiment, which is you're looking at 10 molecules or so interacting with a filament. It starts pulling it out of the trap. As it pulls out of the trap, you detect that, and you apply your own force on it. So you can think about this as a force-velocity relationship for 10 molecules. And the model is able to get that for smooth muscle and for skeletal muscle at 2 different ATP concentrations. As I said, you have to worry about trying to get the number of molecules, and you need to worry about figuring out the stiffness. People have estimates of those experimentally. In the model, the fits to the data are at least within a factor of 1 or 2 consistent with those. So here's some take-home messages. We have a model that works. Unfortunately, it's very, very simple. It only has actin, it only has myosin. It's under simplified chemical conditions, but I think it's a proof of concept. And the idea now is to extend this so that we can actually say something about how real muscle works. Thank you.
Questions for Sam?
Yeah. What do you think is involved in bridging the gap between this individual molecule level stuff and, say, the previous presentation where we want to look at whole muscle, whole body behavior and make better predictions?
So, I mean, there's a huge amount of work that has to be done. So this stuff, right, so let me say that another way. The big thing that you want to get out of the model like that Tan was showing was he wants to get metabolic cost. And he wants something that's very simple to do that, so he says, I'm going to count positive work, I'm not going to count negative work. Having a model that simple would be great. What this can do is say, well, I can get at least a molecular level description of how energetics is happening, and I can come up with some, cobble together something that's at least a little bit more accurate, perhaps, under some situations than that. I don't know if it's going to get down to that level of simplicity, but the dream, I think, is to be able to get a series of models, all of which are self-consistent, which go from this level and get to that level. But to do that, you have to start at this level, and you have to have people who are working at that level, and you need people in the middle. It's not a great answer, but that's a good idea.
It might be a little bit, I might have missed that part, but can you explain the force transducer part, like what created a force?
So these are, I should say, these are not my experiments. But what you do is when you shoot a laser through a very small bead, you hold it in place. And what you can do is you can change the position where the laser is relative to the bead. And it turns out that as long as that distance is relatively small, the force behaves roughly like a linear spring. So you can couple that in as long as the force is small, as it is here. You can figure out exactly what force you're applying on a small ensemble of myosin. Is that?
I mean, what I'm asking is, in physics, we have a very limited number of force we can control. Is it electrostatic, electromagnetic? We should know that to understand the impedance of the muscle side. So,
well, I don't know what force you're talking about. Are you talking about the force in the experiment, or are you talking about just in muscle contraction, where's the force coming from? Yes. Yeah, so you have this strong interaction between myosin and actin. that's presumably partially hydrophobic, partially some electrostatics. But then the force is coming from this large-scale conformational change that occurs in myosin. So myosin undergoes this large rotation of parts of it. Right? So it works like a lever arm and it rotates. And as long as you're holding everything still, then that's going to generate force. And so the thing that's causing it are these sort of, it's the hydrophobic and electrostatic interactions.
So electrostatic is basically,
I mean, partially. I mean, there's also these hydrophobic things that are causing it.
Also entropic things, no?
Yes. So those all come into it. So the hydrophobic, I think, entropy is in that. But yes.
In slide 1, you said hill-like models are not good enough for tone and.
I did not say that.
When you said they're not good enough for macroscopic biomechanics.
I said they're not good enough for some questions. Yes. Okay.
They're not what?
So for some locomotion studies, I think they're not good enough.
Because of what?
Okay. So there's one thing that you can. I have to pin you down somewhere, and that is, what do you mean by a hill model? So you can say, taking the hill force velocity relation, taking the hill force velocity relationship, taking the force length relationship, linear activation, multiplying all of them together, and saying that's your model. Maybe putting springs and dampers in series with it. So having some, right. I think there are certainly things that cannot capture. It can't capture force and hysteretic effects, right? So if you stretch a muscle, it remembers that it was stretched, right? So it can't do that, and maybe that's important for movement. It can't get short-scale transients. You're not going to get all that in a single damper. If you say, well, I can change that damper depending on what I'm doing, all right, you could probably do that. So the point is, I guess, that there are clearly some things that a Hill model can't do.
But do you think they're important for the things that people in this room want to do?
So the question is, what level do you care about? And I think for the most part, what I'm doing is never going to replace the Hill model and Scott Delp simulations. Right? That's not going to happen until 40 years from now, at the least. Right? Because there's such a huge gap between the molecular level and the large scale that bridging that gap in any sort of careful way is just going to take a huge amount of time. So what insights can you get from this? The idea, I think, is that one big insight that you could get is you could understand how muscle works. Right? You can understand more about how muscle works, and maybe that's important. You can understand how muscle works in disease. So that's the big thing, is that what people want to know is they want to know, I have a mutation. How is that going to affect my muscle? Mutation obviously acts at the molecular scale. So if you can characterize that mutation at the molecular scale, with this kind of model, I could, in theory, 40 years from now, predict how it's going to affect simulations.
So, I mean, you carefully described to us Huxley's model, right? So, just in words, can you explain what yours is, how yours is different?
So the short answer is that Huxley makes up how attachment and detachment rates depend on molecular strain. I use measured values of those. And I use measured values of everything at the molecular level to try to do everything that Huxley can do.
But then that's sort of these the parameters, but then the underlying model.
So his underlying model is how chemical reactions behave between sliding surfaces. So in that sense, if I'm looking at chemical reactions between sliding surfaces, I'm using the Huxley model.
Have you thought of modeling muscle fatigue at molecular level? Is it possible? Or?
Short answer, yes. So long answer, people really don't know what causes fatigue. I have a collaborator who is very interested in how phosphate and pH change muscle properties. And as we speak, we're working on a model showing that, that phosphate has this cycle that I just showed you of how myosin and actin interact changes in the presence of phosphate.
Dustin, who's it? And the next speaker, could they come to the front? Yeah. Dustin.
So you mentioned forcible lengthening and energetics as something that Hill model doesn't do well, but I didn't see that you were showing that you can do that well. I'm wondering what your insights is on how your model can get there and how close you might be.
Okay. So one issue is that forcible lengthening of what, right? Presumably what you're interested in is forcibly lengthening of a whole muscle. So what my model can do right now is if you take an actin filament and you pull on it in the direction it doesn't want to go, I can do that. But what happens when a whole muscle is forcibly lengthened? Presumably, some of the sarcomeres, my understanding is there's some evidence that some of the sarcomeres do different things depending on where you are. My model is never going to get that until it knows what a sarcomere is.
All right, we have to wrap it up there, so let's thank Sam.